If you step outside on a clear night and tilt your head back, the sky looks empty and full at the same time. A hush spreads across everything. The stars sit like tiny lanterns on a velvet river. And yet, for all the light, most of what shapes our universe is dark. Not dark like a shadow, not dark like fear, but dark as in. It doesn't glow. It doesn't shimmer. It doesn't whisper to our eyes. We can't see it, but it holds us. This is dark matter, the quiet gravity beneath the visible, the invisible weight that keeps galaxies from spilling apart like sparks from a firework. It's not a ghost story. It's not magic. It's a simple idea with a gentle surprise. The universe contains far more than the stars we can count. And this unseen something, this soft scaffolding, is what gives the cosmos its shape. Imagine a merry-go-round at the park, late evening, crickets humming. If it spins too fast, the children would slide off, unless there's enough force pulling inward to hold them close. Galaxies spin too, grand spirals and humming wheels of starlight. By our ordinary calculations, by what we can see, many of them seem to spin too quickly. The stars at their edges should fly into the night, but they don't. They remain. Something is holding them in. We gave that something a name, dark matter. Not because it is evil, not because it hides with intention, but because it neither emits nor reflects light. It doesn't glow in radio waves, or shimmer in infrared, or flash in X-rays. It is quiet. But its gravity speaks clearly through the motions of stars, the paths of galaxies, and the way space itself bends. And here is the simplest way to understand it. If we add up all the glowing things, stars, gas clouds, nebulae, dust, and ask, is this enough to hold the galaxy together? The answer is no. There must be extra mass that doesn't shine. It's as if we are watching a dance through a curtain. We can't see the partners directly, but we read their presence in the steps, the turns, the arcs they trace. The numbers are startling, but gentle to hold. Roughly speaking, all the ordinary matter, the atoms that make up you, me, the oceans, and the stars is only about 5% of the cosmic budget. About a quarter, 27%, or so, is dark matter. And the rest is something even stranger. Dark energy, a kind of elastic push woven into space-time, causing the expansion of the universe to speed up. Tonight, we'll focus on the middle layer, the soft, impatient mass that shapes the skeleton of the cosmos. Breathe in. Think of a spiderweb, silvering dew, strung between branches at dawn. From a distance, you might not see it at all, just how the light catches its pattern. Dark matter is the web. Galaxies are the beads of water clinging to it. Without the web, the water would fall. Without dark matter, the galaxies would not gather so easily, or stay so gracefully arranged. The universe would be a different kind of place, thinner, more scattered, less intricate. But what is dark matter made of? Is it tiny particles passing through us like ghosts in daylight? Is it something more like mist, smoother, with a wave-like personality? Or is our understanding of gravity itself slightly off-kilter, needing a small, careful correction at the edges? We don't have all the answers yet. And that is part of the beauty. Science isn't just a collection of facts. It's a way of listening to the world, of placing your ear on the rail and hearing what's coming before you can see it. With dark matter, the track hums. It hums through the spin of galaxies, through the shapes of clusters, through the echoes from the Big Bang that still warm our skies like a distant memory. Tonight, let's step gently into that hum. We'll move slowly, one soft step at a time, through how we came to suspect dark matter, what we think it might be, and how we're trying to catch it in the act, without rushing, without fear, with the curiosity of someone tracing a finger through starlight on a still lake. First comes a question simple as a breath. If the universe is mostly invisible, how did we first notice? What tipped us off that something large and quiet was standing behind the curtain, holding everything together? The story begins with motion, with the way galaxies drift and swirl and refuse to fly apart. It begins with people looking up and finding that what they saw didn't fit what they expected. It starts with a whisper. The sums don't add up. And beneath that whisper, a promise. Keep listening. There's more. There's always more. If you were to sit in a small observatory, the kind with a sliding roof and the scent of old wood, you might imagine the quiet punctuated by the soft tick of gears and the faint whir of a tracking motor. In the 1930s, under skies dark enough to taste the Milky Way, astronomers used such patient machines to measure the speeds of galaxies. Red and blue shifts, subtle tilts and spectral lines, told them whether a galaxy was coming or going, and how fast. One of those astronomers was Fritz Zwicky, a prickly, brilliant mind with a gift for noticing what others had not. He looked at the Coma Cluster, a crowded metropolis of galaxies more than 300 million light-years away. He found something odd, something beautiful in its stubbornness. The galaxies in the cluster were moving too quickly to be bound together by the gravity of the visible matter alone. If you only count the light, the cluster should fly apart. It didn't. Zwicky called it dunkel mattery, dark matter. His reasoning, though wrapped in the mathematics of the virial theorem and velocity dispersions, was as homely as the merry-go-round under a street lamp. To keep everything together, you need more inward pull than meets the eye. He proposed that the cluster must harbor a large amount of unseen mass. At first, the idea settled like a seed on rocky ground. The data were a bit rough. The tools were young. And the universe is patient. It reveals itself in layers. Not until decades later did another set of observations, made with painstaking precision, turn that seed into a strong, leafy thing. Enter Vera Rubin, moving carefully through the night with her colleague Kent Ford, using a sensitive spectrograph to measure how stars dance around the centers of galaxies. In a planetary system like ours, the further a planet is from the Sun, the more slowly it circles Earth swift, Saturn patient. If galaxies were held together, mainly by the mass of their visible stars and gas, we would expect the same. Stars farther out should rotate more slowly around the center. Rubin's measurements told a different story. The rotation curves of many spiral galaxies were flat. That means stars toward the edge were moving just as quickly as those nearer the center, not slower. Once again, the sums didn't add up. The outer regions should have been taking gentle, slower laps. Instead, they kept pace. Something invisible was adding mass, extending far beyond the faint glow we could see. You can picture it like walking through fog with a lantern. The light reveals a small circle around you, warm and golden. Beyond the circle, there is more ground, more air, more pathway, but the lantern cannot paint it. In Rubin's work, the lantern was our telescopes, and the fog was the limits of light. The flat rotation curves told us far more than the lantern revealed vast halos of mass surrounding each galaxy, spreading out like an enormous, transparent cushion. If stars are the glitter on the ocean, dark matter is the deep water beneath. You feel its presence in the tide, in the sway, in the way the surface behaves. You might never scoop it up in your hands, but the ocean's weight is always there, pressing softly on the shore. Dark matter, by these lights, couldn't be ordinary matter that simply failed to glow. It couldn't be just dim stars, or planets, or cold clouds of gas. We tried that idea hunting for MACHOs, massive astrophysical compact halo objects, big things like brown dwarfs, faint stars, black holes in certain ranges. Gravitational microlensing experiments watched millions of stars for tiny brightening events as unseen objects drifted in front, bending starlight. They found some events, yes, but not enough to account for the missing mass. The invisible weight was not hiding in that way. So we were left with a softer, stranger idea. Perhaps most of the universe's matter is made of particles we don't yet know. Particles that slip through ordinary matter with barely a murmur, like a fine breeze passing through tall grass. They would feel gravity, of course. Gravity is universal. But they would ignore light. They would ignore magnetism. They might be all around us, flooding through your room right now. Each second, dozens, millions, uncountably many yet hardly ever touching. You can almost sense it now. Not a haunt, not a chill, just a comfortable awareness that the quiet space around you is never truly empty. There is structure here, submerged and subtle. The galaxies believe in it. Their motions confess it with every turn. And there is a gentle clarity in our terms. Dark matter is not dark because it absorbs light like a black cloth. It is dark because it neither emits nor reflects the kinds of light our instruments detect. It doesn't have electromagnetic conversations with the universe. It keeps to itself, polite and reserved, yet strong in its influence. It is the friend who doesn't speak often, but whose presence steadies the room. Zwicky heard the first rumble. Rubin traced the rhythm in the spiral arms. Others mapped the quiet pull in clusters of galaxies. Piece by piece, the picture formed. We live within halos of unseen mass, each halo embracing a galaxy like a transparent cocoon, a shelter against the centrifugal urge to fling apart. And yet the mind asks, are we certain the music is coming from an invisible orchestra? Could it be that our sheet music, the laws of gravity, need a gentle correction at long distances? There are ideas like this too, thoughtful and mathematically careful, suggesting that gravity might behave differently in the soft outer reaches of galaxies. If that were true, perhaps we wouldn't need to add unseen matter. Perhaps the dance steps themselves are a little different than we thought. We will come back to that possibility. For now, let's stand in this quiet field, listening to the stars spin. The question opens, wide and inviting. If dark matter is real, how else can we see its hand? And if it isn't, what kinds of patterns should appear when we look with new eyes? The universe answers slowly, like a tide swelling under a flat moon. The next clues come from the way light bends and from the oldest afterglow we've ever seen. Light travels in straight lines, unless space itself curves. Imagine placing a sheet of silk across a bowl. A marble rolled across it will arc gently, following the shape beneath. In the same way, massive objects bend the fabric of spacetime, and light faithful and swift traces those curves. Einstein called it general relativity. Nature calls it sunrise and lensing, and the soft arcs of galaxies that appear where none should. Gravitational lensing is the universe's own optical trick. When a massive cluster of galaxies sits between us and a more distant background galaxy, the cluster's gravity can bend and magnify the background's light. We see stretched, arc-like images and sometimes elegant circles called Einstein rings. These lenses are not just beautiful, they are scales. By mapping how much the light bends, we can weigh the matter responsible, even if that matter is invisible. Time and again, lensing weighs more than light suggests. The arc's curve says, heavier, while the stars and gas say, lighter. The difference is the dark matter. One of the clearest, quietest proofs sits in a system called the Bullet Cluster 2 galaxy clusters that have passed through each other like silent ships in a night sea. The hot gas clouds, ordinary matter glowing in X-rays, collided and slowed, piling up like mist building on a window pane. But most of each cluster's mass sailed through with little friction. When astronomers mapped the gravitational lensing in the aftermath, they found something striking. The peaks of mass were offset from the hot, visible gas. The invisible matter, whatever it is, passed through with the galaxies. The gas lagged behind. If dark matter were merely gas we couldn't see, it would have collided and stalled like the X-ray loud clouds. It didn't. The bullet cluster says, in calm, measured tones. The bulk of the mass is something that hardly interacts with ordinary matter at all, except through gravity. It is there. It can be weighed. It simply refuses to light up. Meanwhile, the oldest light in the universe, the cosmic microwave background, CMB, whispers the same story. This is the afterglow of the Big Bang, now stretched into microwaves by billions of years of cosmic expansion. Its faint ripples, the tiny temperature variations mapped by satellites like COBE, WAMAP, and Planck, are fossilized imprints of sound waves that moved through the early universe when it was a hot, smooth fluid. The pattern of those ripples tells us about the ingredients of the universe, as it was just 380,000 years after its beginning. When we fit the pattern peaks and troughs like a gentle, ancient heartbeat, we find that ordinary matter alone cannot explain it. The heights and spacing of the ripples demand additional, non-light coupling matter. Dark matter steadies those primordial waves, adding gravity without participating in the glow. It allows structures to grow, first small clumps, then larger filaments seeding the cosmic web we see today. Picture the universe cooling, the first atoms forming, gravity tugging and coaxing matter together. If there were only ordinary matter protons, electrons, the familiar family, it would cling to light for too long, resisting collapse into early clumps. Dark matter, being aloof from light, began pooling sooner. It made wells, soft valleys in the gravitational landscape. Later, ordinary matter fell in, like rain into lakes already waiting. In time, stars ignited, galaxies spun, and the web brightened at the knots. From lensing to the CMB to the distribution of galaxies across space, those slow, lovely ripples, called baryon acoustic oscillations. The evidence leans the same way. A quarter or so of the cosmos is made of something non-luminous and gravitating. A scaffold, a backbone. So what is it? Our first guesses turn to simple, elegant ideas. Perhaps dark matter is made of new particles that interact so weakly with ordinary matter that they slip through us unnoticed. The family of candidates is wide, but one of the favorites for many years was the WIMP, a weakly interacting massive particle. The name is whimsical, but the logic is clean. If the universe began hot and dense, a particle with certain masses and interaction strengths would naturally freeze out at just the right abundance to match what we infer. It's called the WIMP miracle, a neat coincidence between particle physics and cosmology. To find WIMPs, scientists built quiet rooms a kilometer underground, away from cosmic rays. Inside, They placed vats of ultra-pure liquid xenon, or crystals, kept at whispering temperatures. The idea is simple. Wait for a dark matter particle to bump into an atomic nucleus and cause the faintest scintillation of light or vibration. Detectors like Xenon, Lux, and Lux Zeppelin, Panda X in China, and Super CDMS use layers of shielding and sensitive electronics to catch these rare taps. So far, the taps have been quieter than hoped. Each year, the detectors grow more sensitive, the noise drops lower, the search narrows. Parameter spaces are crossed off. Every no is a gift. It tells us where not to look and where to turn our ears next. The Large Hadron Collider has also looked for signatures of dark matter in the debris of high-energy collisions missing energy that might hint at particles slipping away unseen. Again, nothing confirmed yet. Other possibilities call gently from the edges. Axions, for instance, are hypothetical particles born from a neat solution to a mystery in the strong nuclear force. If axions exist and are light and plentiful, they could behave like a very cold, very gentle field filling space, subtly wiggling in tune with hidden radio notes. Experiments like a DMX and Haystack listen with superconducting resonant cavities and quantum amplifiers, hoping to hear axion-induced whispers converting to microwaves in the presence of a magnetic field. There are sterile neutrinos, relatives of the ghostly neutrinos that stream from the sun in nuclear reactors, particles that barely interact with matter as it is. There is the idea of fuzzy dark matter, ultralight particles whose wave-like nature spreads them out over thousands of light years, smoothing the inner cusps of galaxies into cores. There are ideas of self-interacting dark matter, whose whisper-weak collisions could soften galaxy centers and reshape orbits without shining. And yes, there are modifications to gravity, careful and clever reworkings of the rules we use to add up forces in the far reaches of galaxies. Some of these schemes, like modified Newtonian dynamics, can reproduce the rotation curve surprisingly well by tweaking the way gravity behaves at low accelerations. But they strain against the weight of the other evidence. The bullet cluster, the CMB, the way galaxies cluster across the sky. They sing in certain rooms and grow quiet in others. Through all this, the universe remains patient. It lets us try keys in many locks. It watches us build quiet chambers in mountains and tune radio ears to the hiss of emptiness and parse the tangled arcs of lensed galaxies with delicate math. It allows us to ask the same question again and again, with better instruments and deeper calm. What is the quiet gravity made of? And the question grows softer, like the fade of day into blue hour. If we find it, will the universe feel different? Or will it simply feel more complete, as if a long-held breath is finally exhaled, and the shape of the room makes sense? There is one more way to feel the presence of the invisible. Not by catching a particle, but by watching how the universe's grand patterns form from ripple to web, from web to galaxy. The shapes we see, those filaments like frost across the dark, are the handwriting of dark matter. And hidden in that script is the signature of its nature. But we have to read slowly. Think of a winter window breathed upon. A trace of moisture condenses, and with a finger, you draw delicate map lines becoming rivers, intersections becoming towns. In the universe, dark matter grew first. It traced the web, laid down the channels along which ordinary matter would flow and settle. The galaxies are the towns. The clusters are the cities. The filaments are the roads and rivers that connect them. Computer simulations, run on supercomputers humming like distant bees, take the laws of physics we know, and show how structures grow from the infant universe to today. Start with the tiny ripples seen in the cosmic microwave background. Add cold, collisionless matter particles that move slowly compared to the speed of light and rarely bump into each other. Let gravity perform its quiet ballet for billions of years. The result? A cosmic web that looks uncannily like what we observe with surveys of galaxies and clouds of hydrogen. It's not proof, but it's a strong melody aligning with our instruments. Zoom in. The simulations show dark matter halospherical cocoons surrounding galaxies, growing by merging and accreting, like snowballs rolling downhill, gathering flakes. They predict certain patterns: how many small satellite halos there should be, how mass is distributed in the center versus the outskirts, how the halos' shapes trace their histories. Observations, with all their beautiful mesances, match many of these notes. And yet, some notes are off, or at least complicated. The missing satellites puzzle wondered why we see fewer small galaxies around the Milky Way than early simulations predicted. The cusp core question asked why some dwarf galaxies seem to have gentle, flat density centers rather than sharp cusps. The too big to fail issue pointed to simulated subhalos that seemed sturdy enough to form stars, but don't appear to have visible counterparts. At first glance, these felt like stumbles for the simplest dark matter picture. But galaxies are not just dark matter. They are gas and starlight and supernova winds. They are feedback, the push and pull of star formation, and black hole energy stirring the pot. Imagine a pot of thick soup, bubbles rising and falling, eddies reshaping the distribution of carrots and beans. In many updated simulations, those internal burbles stellar feedback can soften cusps into cores and prevent some small halos from ever lighting up, bringing predictions closer to the sky we see. Small-scale problems become laboratories, places where the details of dark matter and the life cycle of galaxies dance together. Still, the specifics matter. If dark matter were slightly warm, not literally, but possessing higher initial speeds, it might not clump as aggressively on the tiniest scales, naturally reducing the number of small halos. If it interacted with itself more than once every cosmic age, it could redistribute its inner mass and create cores. If it were ultralight, wave-like, it would smear out on small scales, painting galaxies with soft centers. Each possibility leaves a fingerprint in the web, a signature in the population and motion of small galaxies, and in the swirls of stars torn from them. Astronomers read these signatures like wind text on tall grass. The Gaia satellite, measuring the positions and motions of over 1 billion stars with exquisite precision, has uncovered streams in our own Milky Way stellar rivers left behind by dwarf galaxies and clusters that were stretched and stirred by our galaxy's gravity. The paths and wiggles of these streams can reveal lumps of dark matter, like invisible stones beneath the current. Future maps will turn these stream ripples into measurements. How clumpy is the halo? How grainy is the quiet gravity? Elsewhere, weak gravitational lensing tiny. Statistical distortions in the shapes of millions of distant galaxies lets us map dark matter in swaths of sky as softly as a painter washes ink. Surveys like the Dark Energy Survey, Hypersuprime Cam, and forthcoming Euclid and the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will draw maps of the invisible, revealing how matter has pooled and stretched over cosmic time. The way that pooling evolves is a lyre string plucked by dark matter's nature. Heavy, Cold strings hum one way. Lighter, warmer strings hum another. And all along, patient experiments in basements of mountains and bowls of radio silence turn their dials, refine their whispers. Axion haloscopes tune through frequencies with the tenderness of someone searching for a favorite station. Ultralight dark matter searches use atomic clocks and interferometers, asking if fundamental constants jiggle ever so slightly as a dark field washes through. Helioscopes gaze at the sun, seeing if axions convert to X-rays in strong magnets. Even gravitational wave observatories, in time, may listen for small lensing echoes, tiny time delays that betray compact clumps of dark matter drifting across their lines of sight. Meanwhile, we keep honest by entertaining alternatives. Modified gravity is not a stubborn refusal to accept the unseen. It's a test of whether a tweak to a law can compress these diverse observations under a single umbrella without new particles. Some versions match galaxy rotation with elegance, connecting the acceleration scale where anomalies arise to delicate relations between visible matter and rotation speeds. But galaxy clusters and the CMB and the bullet clusters offset push back. To fit all of them, the modifications grow intricate, sprouting extra fields that begin to look suspiciously like dark components. The universe, with quiet humor, seems to prefer the simpler thought. There is more matter than meets the eye. There is humility here. We are small, and our senses are geared to warm-blooded lives. The color of ripe fruit, the direction of wind before a storm, the sound of a friend's voice. A cosmos hums on scales and in keys that our bodies did not evolve to hear. We build ears where none existed. Detectors colder than winter's heart, mirrors steadier than the calmest pond. Algorithms that sift starlight like fine sand. Dark matter is not an indictment of our senses. It is an invitation to grow new ones. And then there is the meaning each person carries away. To some, dark matter is a gap, a cliff edge in our understanding. To others, it is a handrail we can't see but trust, because without it the stairs don't hold. To me, it feels like the breath between notes in a lullaby, the part you don't hear that makes what you do hear coherent. The unseen doesn't negate the seen. It completes it. It holds the bright together. Tonight, as you listen, notice how calm knowledge can be. The universe is not rattled by our uncertainty. It drifts forward, stars spinning, clusters gliding, filaments stretching, while we, curious and gentle, reach up like children to trace its lines. We have come far, from Zwicky's first estimates to Rubin's firm curves, from lensed arcs to microwave ripples, from mountain labs to satellites that weigh the sky. The map is not yet complete, but the directions are clear. In the quiet ahead, new instruments will open. New corners of parameter space will dim. A detection might arrive like a feather, landing barely a sound, but changing everything. Or it may be a slow dawn, a dozen clues aligning over years into a certainty too graceful to deny. Either way, the path is soft beneath our feet, and the next turn lies just ahead. Let's stand now on a balcony of time and look forward with unhurried eyes. The night is wide. The instruments rest, waiting to wake. Soon, the Vera Rubin Observatory will begin an elegant sweep of the southern sky, returning to the same fields again and again, watching faint galaxies wink and sway. Its legacy survey of space and time will trace weak lensing patterns with unprecedented detail, drawing the invisible in softer, finer strokes. Europe's Euclid satellite, already afloat, will map billions of galaxies, their shapes and distances, building a 3D relief map of how matter has clumped across cosmic history. The Nancy Grace Romang Space Telescope will join, its wide eyes poised to notice the smallest twitches in the deep. On the ground and underground, patient sentinels continue. Lux Zeppelin listens in the dark. Xenont and Panda X refine their inner silence. SUPERCDMS chills silicon and germanium to a hush, hoping to feel a passing nudge. If the WIMP family is real, these instruments stand a strong chance of hearing the soft knock. If it is not, their quiet no will be just as valuable. A polite closing of one door that nudges us to try another. For axions and ultralight fields, a DMX adjusts its tuners like a musician, coaxing the right pitch. Haystack embraces quantum tricks to reduce the hiss of measurement itself. DM radio explores lower frequencies, where ultralight whispers might live. IAXO, the proposed International Axion Observatory, dreams of catching solar axions, converting into X-rays under the spell of powerful magnets. Atomic clocks, already the most precise timekeepers we have ever built, compare notes across continents, searching for coordinated wiggles that could betray a dark wave passing through Earth. Elsewhere, radio arrays like the Square Kilometer Array will chart hydrogen's faint emission across space and time, showing how the first structures rose under gravity's hand. CMBS-4, the next generation of cosmic microwave background experiments, will sharpen the ancient ripples, letting us weigh the cosmic ingredients with even finer fingers. And gravitational wave detectors, with ears pressed to the fabric of space-time, may one day notice tiny lensing effects, subtle blurs in a chirp that reveal compact dark clumps crossing the line of song. Each instrument is like a lantern placed along a sleeping path. Taken together, they trace a gentle arc toward clarity. Discovery may arrive not as a drumbeat, but as a quilt, many small squares sewn together, warm and patterned, telling a story at a human pace. And what if, after all this, dark matter turns out to be a surprise from the edge, an idea we haven't yet framed? Science has room for that too. It does not break when old ideas bend. It can hold contradictions lightly while evidence gathers. A universe has been patient for 13.8 billion years. It can wait a few more to show us the right angle to look from. In the meantime, there is comfort and quietly joy in what we already know. We know that the visible is not the whole. We know that the galaxy's grace is not accidental. We know there is a scaffolding, a gentle strength, holding the luminous things in place. We know that the same gravity tugging at your feet as you stand on Earth is part of a wider, deeper tug that sculpts the cosmic web. There is also a tender, personal echo here. Think of the invisible structures in your own life, the habits that hold you, the promises you keep to yourself, the relationships that don't show up in your calendar but shape your days. The way a quiet friend steadies the room. The way a routine tea at dusk, a few pages of a book gives your mind a place to rest. Dark matter is not a metaphor for these things, and yet the resonance is there. Unseen does not mean unreal. Quiet does not mean weak. Much of what matters most is felt through its effects. When you look at the night now, perhaps you'll picture halos, the Milky Way nested within a vast, transparent sphere of mass, extending well beyond the farthest star you can see. Perhaps you'll imagine the local group of galaxies drifting together in their shared dark halos, moving through space like lanterns on a slow river. Perhaps you'll sense the cosmic web, a lace that stretches across hundreds of millions of light years, its knots decorated with clusters where thousands of galaxies rest, like villages at crossroads. And perhaps you'll feel something else too, ease. The understanding that not seeing is not a failure. It's an invitation. We built senses for a particular world. Now we are building new ones for a larger one. The unknown is not a void. It's a field, a meadow, waiting for us to walk across it, step by gentle step. Zwicky, with his early suspicion. Rubin, with her careful curves. The lensing arcs. The microwave ripples. The silicon crystals and xenon lakes in the dark. The radio cavities listening for imaginary notes that may yet prove real. All of them are chapters in a bedtime story that stretches from mountain domes to deep tunnels, from dry equations to the shimmer of galaxies. All of them are lanterns around our sleeping path. The quiet gravity remains, regardless of what we name it. It holds the spiral arms, balances the orbits, and lets the universe grow intricate without falling apart. It is not here to frighten. It is here the way a foundation is here out of sight, holding up the rooms where we live and dream. As the night deepens, breathe softly. The stars are not alone in their work. The web is under them, and beyond them, and through them. We are held, too, by laws and patterns that care nothing for us, and yet create a stage on which life can rise, wonder can bloom, and curious minds can look up and whisper, "I don't see you, but I feel your pull." Thank you for holding us together. If you'd like to keep wandering these quiet paths with me, unhurried, curious, lantern in hand, you're welcome here. Subscribe if it feels good, rest when you need to, and join again when the sky calls. We'll keep listening to the universe together, calmly, one soft mystery at a time.